This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're diving into a fascinating JavaScript applet simulation designed to illuminate the nuances of numerical methods for solving ordinary differential equations. It's a powerful tool for visualizing complex mathematical concepts.
Indeed, the ability to visually represent these abstract processes is key to understanding how different numerical methods approximate solutions to differential equations. It bridges the gap between theory and practical application.
And it does so in a remarkably intuitive way. The simulation allows users to directly manipulate parameters and observe the impact on the accuracy of the solution.
Precisely. This interactive element is crucial. It allows for a deeper understanding than simply reading about the methods in a textbook.
Let's start with the core of the simulation, the types of differential equations it handles. The simulation focuses on a specific type of differential equation. Can you elaborate on that?
The simulation centers on first-order, linear, explicit ordinary differential equations. These are a fundamental class of ODEs, providing a solid foundation for understanding more complex systems. The simplicity allows for a clear demonstration of the numerical methods without getting bogged down in excessive mathematical detail.
And what specific example is used within the simulation to illustrate these methods?
The simulation uses the exponential function, represented by the differential equation dr/dt equals y. This is a classic example because its analytic solution is well known, y0 et, allowing for a direct comparison between the numerical approximations and the exact solution. The simplicity of the equation makes the visual comparisons particularly clear.
So what are the three numerical methods being compared in this simulation?
The simulation compares the Euler method, the Hewn method, also known as the improved Euler method, and the Runge-Kutta method, specifically the fourth-order RK4 method. Each method offers a different approach to approximating the solution, with varying levels of accuracy and computational complexity.
Can you briefly describe the differences between these methods?
The Euler method is a first-order method using the derivative at the beginning of an interval to estimate the function's value at the end. Hewn improves upon this by averaging derivative estimates at the beginning and end. Runge-Kutta takes this further, using a weighted average of derivative estimates at multiple points within the interval for significantly higher accuracy.
How does the simulation visually represent the analytical solution, and how can users modify it?
The analytical solution is represented graphically as a smooth blue curve. Users can modify the initial value, y0, using a slider, which directly affects the shape of the analytical solution curve and, consequently, the accuracy of the numerical approximations. This allows users to explore the impact of different starting conditions.
And how are the results of each numerical method visually represented?
The numerical approximations are shown as discrete points, blue for Euler, green for Hewn, and red for Runge-Kutta. This allows for a direct visual comparison of the accuracy of each method against the analytical solution. A second window displays the relative residual difference, providing a quantitative measure of the error.
What parameters remain constant across all three numerical methods in the simulation?
Several parameters remain constant: the initial value, at x0, the range of variables, the number of intervals, n, and the width of the intervals, delta. Keeping these constant allows for a fair comparison of the methods themselves, isolating the impact of the algorithmic differences.
Let's delve into the specifics of each method. In the Euler method, how is the next y value calculated?
In the Euler method, the next y value, yeii, is calculated using the formula yei1 equals yei1, the delta derivative ei1. This essentially uses the slope at the previous point to extrapolate to the next point. The simplicity of this formula contributes to the method's low computational cost, but also its lower accuracy.
How does the Hewn method improve upon the Euler method?
The Hewn method refines the approximation by using an average of two derivative estimates, one at the beginning and one at an intermediate point within the interval. This averaging process leads to a more accurate approximation than the simple extrapolation of the Euler method.
And how does the Runge-Kutta method further enhance the accuracy?
The Runge-Kutta method employs a weighted average of four derivative estimates at different points within the interval. This sophisticated averaging scheme significantly reduces the error, resulting in a much more accurate approximation, especially for larger interval widths. The increased accuracy comes at the cost of increased computational complexity.
Let's discuss the relationship between the number of intervals, n, and the accuracy of the approximations.
As the number of intervals, n, increases, the accuracy of all three numerical methods generally improves. This is because a larger n leads to smaller interval widths, delta, resulting in more precise approximations of the function's slope at each step. However, increasing n indefinitely is not practical due to increased computational costs and potential for round-off errors.
Z-simulation uses the exponential function as an example. Can it be used to solve other types of differential equations?
Yes, the simulation's code is accessible through the EJS console. Users can modify the derivative calculation within the code to solve different differential equations. The places where modifications can be made are highlighted in the code itself, making it relatively straightforward to adapt the simulation to different problems.
Let's summarize the advantages and disadvantages of each method.
The Euler method is simple and computationally inexpensive, but its accuracy is limited. Hune offers improved accuracy at a moderate increase in computational cost. Runskuta provides the highest accuracy but requires the most computation. The choice of method depends on the desired balance between accuracy and computational efficiency for a given problem.
The simulation emphasizes the concept of an initial value problem. Can you explain this concept?
An initial value problem involves solving a differential equation given an initial condition, a known value of the function at a specific point. This initial value serves as the starting point for the numerical methods, determining the trajectory of the solution. Different initial values will lead to different solutions, even for the same differential equation.
What is the value of a simulation like this in teaching and learning about numerical methods?
Simulations like this are invaluable educational tools. They provide a dynamic and interactive way to learn about abstract concepts. The visual representation of the numerical methods and their comparison to the analytical solution makes the learning process more engaging and intuitive than traditional methods. Students can experiment and explore the impact of different parameters, fostering a deeper understanding of the underlying principles.
So in essence, this simulation offers a powerful and accessible way to grasp the complexities of numerical methods for solving ODEs.
Absolutely, it's a valuable tool for both students and educators, bridging the gap between theoretical understanding and practical application.
That was a great discussion. Thank you for your insights.
Oh,